Hey, welcome back. So, in the last two episodes, we covered the derivation of a function, and we summarized that the when you differentiate an equation, or when you take the derivative of a function, right? Any given function, in essence, all you're doing is finding the slope of the line for that function. And in this case, most of the functions don't create nice straight lines. And in our example, what we used was the use of walking or jogging based on our smartwatch data. And we surmised that uh, our, our performance curve, the result of our walk or stroll, was similar to the function 2 times square root of t. So if you have a function, the distance covered over time, you know, um, that represents this line. It looks something like this. So you notice over here, just to recap, so we have distance covered on the y-axis and time elapsed on the x-axis. And 2 times square root of t will give us this line. We plotted out the numbers. We plotted in hour 0, 0, 0. Hour 1, we have 2. And we just went and plotted it very simply. And also we figured out, we did a quick example of trying to figure out the average speed that we were walking for the 8-hour duration, right? And I think we came up with 0.7 or something like that. And the average speed being the rise over run, or just finding the slope of a line for the time elapsed that we were concerned with. So we've taken we hadn't derived it yet, but just taking a very simple algebraic equation, we figured out the slope of this line. So we figured out the average speed, and we applied the power rule to this function, which gave us another equation. We're going to put it down here so it doesn't. When we take the derivative of d of t, we end up with 1 over square root of t through the power rule. So that's kind of where we stop. And just to put closure on this issue, I'm going to cover how, given distance and given time, we can derive velocity or speed, right? And by taking the derivative of the original function, line function, that covers these two factors. Now, I'm going to illustrate now again. If we take the derivative of the velocity, we'll end up with acceleration. All right, so this kind of ties into the whole Newtonian physics of kinematics, the first semester of physics that you're going to come across, that you may have come across already. So if you're watching this, I hope you're watching this not because you're cramming for an exam, because this is more just for our casual understanding of the subject. So if we differentiate this equation again, all right, so if you notice, this is equivalent to t to the 1/2, negative 1/2, right? Because it's in the denominator. So if we differentiate this again using the power rule, all right, we're going to have d double prime t will be equal to, we'll bring this down, negative 1/2 times negative 1/2 minus 1 t to the negative 3 over 2. So this is what the d double prime of t will end up being. So given a distance and time equation, we were able to derive the rate of change, find the slope of this line through this formula. So this formula would be so maybe if we go back to, let's back up a little bit. All right, when you find the derivative of something, right, usually we're looking for the slope, right? So this is the delta d, and this over here is the delta t, change from here to here. So the delta can change depending on the time frame you're looking at. And I know I started with the series with not wanting to talk about limits, and because I think limits are it's not intuitive, right? But then once we work the problems backwards, you'll kind of see the logic of why they approach it through limits, because we're going to run into the problem as we start deriving on multiple tiers. So let's graph this out. If we, I have it all in Excel, so I'll just, during post processing, I'll just cycle to the slides so that way you don't have to watch me draw. So t is again in the independent variable line. It's unchanging, right? We can't really affect this unchanging variable. Now, if we were to plot this, instead of plotting d, this will be d prime of t, which means in common language will be velocity, right? Displacement over time. And if we plot this out, you're going to see that the chart is going to look something like this. Oh my goodness. All right, so if we plug in the formula, time d prime of t, or velocity. 0, 1. You plug in 0 here, you'll get an infinite number. You can't divide by 0, right? So this is why, this is one of the reasons why we approach it using limits. So instead of saying 0 that we can't divide into, you'll use something very, very small, and you try to see where it's going towards, at what point it kind of cuts off. It's an asymptotic relationship, so it goes into infinity, right? But so this is undefined. One is 1, 2 is 0.7, 0.57, so if you chart this out, the scale is very small, so we'll make it So at 1 is right up here somewhere. 2 is 0.7. 3 is 0.57. 0.35. So you're going to wind up with the chart like this. So if you notice this chart, what this chart tells you is, in the very beginning, our slope is pretty steep, right? The slope of the line that runs tangent to this curve. So at 1, it's saying the slope is probably 1. I mean, it's not probably, it is 1. And at 2 is 0.7. So there's 0.7 over 1. So which makes sense, because you could see the velocity, your travel velocity as time progresses is diminishing, is getting lower and lower. But what you started off really, really well. But between 0 and 1, when we went from 0 velocity to 2 miles per hour, math has problems computing the boundary conditions. So that's just one of the shortfalls of math, and that's why we study. Well, that's why most curriculum will make you study limits before diving into differentiation. All right, so to take one step further, let's chart out acceleration. So the same goes for the acceleration. The acceleration, instead of starting at 0, let's just start at 1, 2, 3, 4, 5, 6, 7, 8. So the acceleration, whereas velocity, d prime of t, velocity, d double prime of t. This again is t. If you plot this out, you're going to get a graph that looks something like this. At 1, it's going to be at -5. And jumps to 0.17. 7. So this line will tell you will predict the slope, the instantaneous change of distance over time at this particular point, right? And whereas when you double differentiate something, this line then describes the slope of the velocity line. So let's just see if we can get some sort of intuition from it. Notice it's negative, right? It's negative 0.5. That means at time 1, it has a negative acceleration. Even though it has a positive velocity. But that's because it's slowing down. So acceleration is not a constant thing. Acceleration is it's a time squared function. So that's why it's not very intuitive. We have to kind of just trust in the graph and then trust in the math. So whereas the velocity chart will tell you the instantaneous velocity of our distance to time function, the d double prime of t will give you the slope of the velocity line. and tell a story of your instant velocity. Well, the instant acceleration or deceleration at that point in time. So this will give you the slope of this line. This gives you the slope of this line. You notice the slope is in the negative direction velocity, and it eventually goes to approaches zero, but never gets to zero. And acceleration, even though it's a negative slope, notice it's gone upwards towards zero. So I know it's kind of counterintuitive, but and this is the basis, derivation is the basis of the 4 basic kinematic formulas that you will come across in Physics 1, in any physics curriculum. And, that's it. So with that, I'm going to wrap up this discussion on limits. No, wait a second before I do that. All right, so again, limits. So we study limits because of these exceptions. The point where you go from 0 to 2, right? And when you derive it, you end up with a lot of these factors or variables in the denominator. And when you try to divide something by 0, it doesn't work. So that's why we just study limits to kind of approximate. Like if we just run this line as far back as we can, where would it end up? And in the case of finding slopes, so when we find slopes, we're looking for the slope is rise over run, right? Like that's pretty much how we visualize it in the field. But in the case of a graph, it's the delta of y over delta of x. And when something is okay, so in delta of y, delta of x, and that's why a lot of times for differentiation, in addition to y prime or the specific function, y prime of x or f function prime of x, or in this case, it would be the d prime of t, which we kind of said here. These are all the same things. Delta distance covered over delta time elapsed. Difference d of major D and d of t over d of t. So all these symbols describe, differentiation. So rate of change is, again, is the name of the game. All right. This is the original function. D prime of t describes a rate of change of this function. D double prime of t describes the rate of change of this function. So, yeah, the rate of change of velocity. This describes the rate of change of distance. And yeah, I think we're going to go and close up the discussion. And I know right now it probably seems rather abstract, but I'm not going to go too much more into the kinematics But when I start talking about statics and dynamics and force equations, this is going to come back and haunt this again. So uh, until then, let's go on and talk about other subjects in calculus.